All right, welcome back, class. So, hoped to be better by today, not better by today. On Friday, in fact, the plan is to do an activity rather than a lecture. So, I hope I'm better by then, but if I'm not better by Friday, we'll be able to have an activity, which I'll be able to send you the details of, and you can turn it in. So, we won't have a video for Friday in any event. Uh, hope. I very much hope I'm better by next week. Let's not let this drag on anymore. But anyway, for today, you get a video. For Friday, there's going to be an activity, so you can look forward to that. What are we going to talk about today? Today, we're going to talk about quadratic models. So last time we talked about linear models. And linear models are great for modeling things where the data looks linear. However, they're not so great for modeling things where the data doesn't look linear. What does linear really mean, or what does it mean to look linear? Really, the key to being linear is that something is linear if it is changing at a constant rate. Really, that whole idea of a constant rate, that's just the name that we give, or that's just another way of saying the idea of slope. Lines have a slope. Now, a lot of real-world data sets, as we saw last time, do have a linear shape, or at least a roughly linear shape. We saw that being the case with the college tuition data. And we saw that being the case with the cricket chirping data. But many, many things will not have a linear shape. So for example, here, move my camera over to here. So for example, here is the number of COVID cases in the US starting in March and going March of 2020 and ranging through 2023 when the US stopped tracking it. So you can see here, this shape is not at all linear. And if you try to sort of draw a line on top of this, it's not going to really capture any of it at all. Now, what you might be able to do is you might be able to pick some specific section of it, some specific time. You might be able to say, like, maybe there is a nice linear shape through just this section or through just this section, that kind of thing. But the overall shape of this data is much more complicated. And a lot of things that we're going to look at are going to naturally tend to have more complicated shapes. So one of the things we're going to do in this course is talk about a bunch of different shapes that you could choose for your models, which will let you capture more complicated things that are happening. Now, in terms of the next thing after linear, a really natural choice is quadratic. So you probably are used to thinking of a quadratic as being something ax squared plus bx plus c, which is perfectly fine. But for us, just like we did with the point slope, it's going to be helpful to write it a slightly different way. We're going to tend to write it instead as y equals a times x minus h squared plus k. The reason why I'm doing it this way is, again, because this is going to have a vertex at hk. Oops. That's sort of the tip of the parabola, if you like. And a here dictates how sharply the parabola sort of points up or down, how pointy it is. And whether a is positive or negative dictates whether the parabola points up or down. So a greater than 0 means the parabola points up, and a less than 0 means the parabola points down. So we're going to be able to use this to capture some data sets that look more complicated than our previous linear models. So let's start by looking at this baseball angle data set. So what this data set is giving is for a bunch of different hits of a baseball off of a baseball bat, how far the baseball ended up traveling based on the angle at which the baseball hit the bat. So we have a wide range here of angles, and the angles given here in degrees, and then a wide range here of distances. So if we go ahead and just copy that into Desmos, as we are wont to do at this point, let us pull up There we go. This was graphing calculator. If we want to pull this up like this, then you can see already, even before I get rid of the grid, that we have this sort of nice shape that looks kind of like a parabola. And again, we should label our axes. So this is the angle in degrees, and this is the distance in feet. Right. And so we have this shape. And so what we want to do here, and we want to start with trying to fit a quadratic model to the data. And before we even do that, maybe we should just ask ourselves, where does the vertex of this data appear to be? Or where does the vertex of this parabola appear to be? And so the vertex, remember, that's supposed to be sort of the pointy bit at the top. So that's going to be somewhere about here. So somewhere between these 2 points, probably. So somewhere between 40 and 45. So let's maybe try and guess that the x-coordinate of the vertex is maybe 43, and the y-coordinate, well, both of these have y-coordinate about 285, so that maybe the vertex is a little higher. Maybe let's go 287. Let's try that. So again, we're just eyeballing it, but we're eyeballing that the vertex appears to be somewhere around 43, 287. And we're going to use that to try and write down what our model is going to look like. Okay. So let's write in our parabola. So it's going to be y equals a times x minus 43 squared plus 287. Okay. Again, that's only because of the model that we wrote down. Remember, it was this. It was a times x minus h squared plus k when the vertex was h comma k, and we estimated our vertex to be 43, 287. So if we head back over here, we have this. Can add our slider here. Now, of course, you might notice our parabola points down. I started here at a equals 1. That's pointing up. So I should certainly slide it down into the negatives. And I can kind of try to eyeball this somewhere in that vicinity. Now, I'm noticing here, actually, this is pretty close to what I'm looking for. It would look a little better if I slid it a little bit to the left. So if I made the vertex, say, 42 instead. Oops. Like that. That may look a little bit better. But yeah, that, if I'm looking at it, that looks honestly not too bad. I'm gonna try seeing if I like it better if I slide it over one more. I think I like that even better, actually. So here's our, I'm just going to go ahead and declare that is our quadratic model here. So I'll write that down. So our quadratic model here is the distance is minus 0.2 times theta minus 41 squared plus 287. Okay. Okay. Again, notice I called my variables here d for distance and theta because theta is a sort of angly kind of choice. Theta is our usual choice for an angle. Remember here, theta is in degrees. Why I spelled out theta rather than writing the theta symbol, the world will never know. All right. So let's ask ourselves now, when I'm sort of thinking about this, what does this vertex of this parabola here mean? What does the vertex mean in real world terms? So what you can think about here is, if you imagine here that this description, this parabola is giving me an accurate picture of how far the baseball is traveling based on what angle I hit it at, then what this is telling me is, because this vertex here happens at the maximum, this is telling me what the furthest distance that I can hit it at. So let me write that down. So our vertex ended up being here at 41,287. That's where the vertex we actually put in our model. What does that mean? That means that the ball travels the furthest, and the angle is 41 degrees. And in that case, it travels 287 feet. The vertex of a parabola is always going to be either a maximum or a minimum, depending on whether your parabola points up or down. So in this instance, it's definitely a maximum that we are seeing here. And so we can see that as the top of our parabola. Now, what can we do with this? We can use this model to do exactly the same kinds of things that we did with the linear model. And so now we can do things like, for example, if we hit the ball at an angle of, and let me pick 55 degrees, how far do we estimate it would travel? Well, once we have our nice model here, then we can answer this question just by plugging in the 55 degrees in for theta here. So we get minus 0.2 times 55 minus 41 plus 287. There's a squared there that I didn't copy. Would make the answer not come out right. Can hop over to the scientific calculator and just type that in. Minus 0.2 times 14 squared plus 287. And it will tell us the answer is 247.8. And so that is our answer here, 247.8 feet. Now, we can look and see, how does that compare to our data set? Does that seem reasonable in the context of our data set? And so 55 is somewhere between 58 and 50. And so with 55, we saw we were in the range of 244. With 50, we saw we were in the range of 270. This is between those two. So this at least seems broadly reasonable. And what we just did there when we came up with this, just to put it in the graph for you, is we said, okay, if you hit it at an angle of 55, then you're going to end up at 247.8. We just used this dashed line, which is our model, and we just estimated, well, if the point were to fall exactly on the dashed line, where would it end up? And the answer is it would end up here. Okay, and so what we're doing here when we make this model is we're saying, well, we know all the points end up pretty close to the model. So when we don't have actual data, we can just use the dashed line instead. So we can estimate here, for example, that at 55 degrees, that we'd end up traveling this 247.8 feet total. Realize, by the way, here I had my camera over at the 55 here. Again, the 55 down here on this x-axis, that's corresponding to this 55 up here. Now, we can equally well do this the other direction. And so we can ask, if the batter wants to hit the ball a total distance of 200 feet, what angle should be used? Okay, so again, now what we're doing is we're specifying, if the distance is 200, what should the angle then be? So we'll write down the equation 200 equals minus 0.2 theta minus 41 squared plus 287. Okay. And now we can solve this equation. So we'll get minus 87 equals minus 0.2 times theta minus 41 squared. Multiply both sides by minus 5 to get rid of the minus 0.2, because minus 0.2 is a fifth. If you prefer, you could just divide by minus 0.2 if you prefer, whatever works for you. Take the square root of both sides. Notice again, I'm not actually multiplying out 5 times 87. I'm just going to leave that to do once I type this into the calculator at the end. So I'm just leaving this as 5 times 87. Note I get a plus or minus when I take a square root of both sides, because if something squares to a particular value, I don't actually know whether it was the positive version or the negative version, because squaring, remember, removes the plus or minus. So whenever you're solving an equation by taking a square root of both sides, you always get this annoying plus or minus that comes in. And so what I get is that theta is 41 plus or minus the square root of 5 times 87. Let's go ahead and see what that is. Okay. And so looking at this, we see that the theta values we get as our answers here are about 20 degrees and about 62 degrees. Right. Note, this plus or minus should be pretty familiar when you're solving a quadratic, because when you're solving a quadratic, you maybe are used to using the quadratic formula. And when you use the quadratic formula, it has that plus or minus in it that makes these two different numbers show up. Okay. Now I want to show you can also figure that out from this graph here. Because what I'm actually asking here, remember the question was, let's just remember what the question was that we just answered. The question was, if we want to hit the ball 200 feet, what angle should we use? We can actually answer that here by saying, well, where on this graph am I hitting 200 feet? And so you can sort of eyeball it here. But actually, if you don't want to eyeball it, you can actually just type in, just flat out, y equals 200. And Desmos will draw it in for you. This is where it's hitting 200 feet. And so you'll see there's two different angles that will cause the ball to be hit 200 feet. And there's this one. And if you click on it, it will give you the exact coordinates of the intersection. So the intersection of these two curves here is at 20.143, which is our 20-degree answer. And over here at 61.85, that is our 62-degree answer. And so you'll notice here, if you're actually answering this question and you have Desmos open, have a graph in front of you, Desmos will just outright tell you, hey, this is how, this is what angle you should use. And then you've got your answer. Sorry, I realize my camera is in the way of something no matter what I do. All I did was type y equals 200 over here. That was what was hidden beneath my camera, was me typing y equals 200. And that told me, okay, where is it at 200 feet? It is at 20 degrees or 62 degrees. Note both of these, both the 20 degrees and the 62 degrees, they're both quite well within the range of the data set that we have. So there's no reason to be particularly suspicious that these numbers will be well off. If we tried to pick something where it was going to end up hitting it, something like, and we're going to end up over here or something like that, then we might become suspicious that maybe our data set's not quite going to be accurate. Or if we were looking for, say, this number of feet, so something like, say, 140 feet instead, then we see there's two answers, but we'd have a lot more confidence in this answer of about 14 degrees than we would in this answer of about 68 degrees, because this one is within the range of our data set, and this one is not within the range of our data set. So keep that in mind. You should always look at sort of how the answers you're giving when you're using your model, how the answers compare to the data you actually have. All right. Next, we're going to look at this data concerning the population of endangered birds on an island. Okay. So this data is giving you a series of years, 0, 1, 2, up to 25. So this is 26 years worth of data. It's giving you their population in thousands. So 19.3 is not 19 and a third of these birds. It's 19,300 of these birds. And so we have biologists here estimating their population in each year. So let us go ahead and pull up a graph of this data. Okay. So first of all, to note, we should label our axes. So we've got bird population on the y-axis. And we've got year here on the x-axis. This is pretty common, by the way, when you're graphing things, to start with an index year of 0. So just whatever year you start studying the birds, you call that year 0, and then you go year 1, year 2, year 3 after that. That's a pretty normal thing to do. Okay. So first thing to note, this is a time series. Because we're giving sort of how this thing is changing over time. And so one of the things we've learned that we do with time series is we usually want to turn on the connecting lines. Okay. Now, you might notice when you do turn on the connecting lines like this, that this data is sort of bouncing all over the place. Okay. And now when you see data like this that's bouncing all over the place, you have to ask yourself why you think that's happening. Okay. And so why is this data bouncy? And now there's two possible explanations. So one of the answers is that the data is bouncing up and down, by which I just mean, like, look at this sharp tick up and down and up and down, and you see that sort of throughout. You might guess that really that's what's actually happening. Like maybe we're sort of having these really extreme swings in terms of, say, like amount of rain or something like that, and that's impacting the bird populations. But you might also suspect that that might be evidence of some errors in the approximation. And when you're talking about estimating populations of birds on an island, that's very likely, because the way that biologists have to estimate populations, they can't sort of count every single bird. They have to make some observations and then try and infer the population from that. And so those observations might well be off in either direction. And so what we're likely seeing here is measurement error. Now, when you think that's what you're seeing, that chunk of measurement error, probably we actually, even if it is a time series, we probably actually only make it harder to see what's happening by including the lines, because the lines are suggesting a trend that we believe probably isn't actually real, namely this sort of this bouncing back and forth. So even if it's a time series, if it has this kind of apparent shape, you might turn the connecting lines off and just look at the shape of the dots to sort of guide you about what's actually happening. Now, this looks, I will say, a lot more like a lot of what data sets you're going to see actually look like, where I can look at this, and depending on how I look at it, I might see very different things in the data set. So let's try and fit this data set with a linear model first. So let's find a linear model for this data set. Okay. So if we're going to try and find a linear model, we again sort of pick something sort of in the ballpark. So something like y equals, and so I'm going to pick m times x minus 15 plus 19.6. Add a slider for m. Okay, but the 19.6 is a little low, certainly. So just because I happened to pick one of the points that was in one of the really low years to sort of start out, so I can go up to, say, 25. Sorry, I was trying to go up to 25. Maybe actually that's still a little low. I can try 30, something like that. Sort of It's a little shallower than that. Something like that. Looks pretty good, except for maybe these couple points up here. But if I look just at this point, if I just sort of cover those up in my mind, this actually looks pretty good as a model of the population. If I'd only sort of like started counting in this year, this would look perfect. So this is one very plausible looking model describing the bird population. So our linear model here works out to be something like birds equals minus 2.1 times x minus 15 plus 30. Okay. So again, if you think about what the story of this is telling, well, remember, what's the slope here? The slope here is minus 2.1 thousands. Remember, because the birds are in thousands of birds per year. And so the story being told here by this model is that the bird population on the island is declining by about 2,100 birds per year. Indeed, the picture here is quite bad. If you, again, remember that this dashed line is how we're sort of predicting this is going, because here we see actually the bird population is supposed to hit 0 in year 29. So indeed, this model predicts that, in fact, the birds will go extinct by year 30. Right. Again, all you'd have to do if you wanted to solve for that algebraically instead of graphically is just take the model that we have here and set the number of birds equal to 0. That is the there are no more birds point. So minus 2.1 times x minus 15. And then you can just solve this equation like you would, sorry, plus 30. And then you can just solve this equation like you would any other linear equation. So you say minus 30 equals minus 2.1 so times x minus 15. And so then you have minus 30 divided by minus 2.1, which I guess just makes it a plus, equals x minus 15. So then you get x. And yes, if I was more awake, I really would have realized this should really be a t because it's a year. So I'm going to go ahead and make this a t retroactively and do that same thing here and here. Somehow I went over how birds should start with b because it's the number of birds and then just randomly used x. But anyway, I'll use t. So my year t should be, when the birds will go extinct, should be 15 plus 30 over 2.1, which if I pull up the scientific calculator here, 15 plus 30 divided by 2.1 is about 29.3. Okay, so that is, if we look at this and we see a linear model and we see that is how we should model it, we end up predicting that after a fairly short amount of time, that we're going to end up with the birds dying out completely. Now, if you were to be optimistic, you would look at this and you would say, well, that's not quite what the data shows. This does a good job maybe of capturing this portion of the data. But there's some data at the beginning that suggests that actually the bird population is declining, but actually the bird population is declining at a rate that's slowing down. The bird population was declining very rapidly at first, but it's slowing down. Now, a linear model can never capture that. A linear model can never capture a bird population which is declining, but is declining more slowly. But a quadratic model can. And so what we can try and do is we can try and find a quadratic model for the bird population instead. Okay, so to do this, again, we're going to write down our form. So first I'm going to hide the linear regression because we don't need to look at it at the same time, but I'm going to leave it there so I can put it back if we want. And then I'm going to take y equals a times. And so if I'm trying to sort of imagine a parabola running through this, I'm imagining the vertex somewhere about here, give or take. So we'll say x minus 25 squared plus, and let's say that that's about, that's about 9, so plus 10 maybe. And we'll add a slider there for a. So I tried to put sort of the vertex down there. Now I've got a slider here. Now my slider is maybe not quite fine enough because of the fact that my slider here is going over quite a wide range. So I'm going to change it to go between 0 and 1 instead so that I can actually look at each of these. And maybe that looks something like that. Maybe I can raise this number up a little bit. So let's try this being 15 instead. Flatten this out a little bit. And now I think that looks not too bad, actually. Somewhere in that vicinity. Maybe I can actually sort of move this over a little bit. And then maybe make this a little bit steeper. Yeah, that looks pretty good. So I've now ended up with my model here being birds equals 0.205 times t minus 22 squared plus 15. So that is where I have now ended up with my bird model. This is my population model here. So in this version, here we have a vertex at, and again, you can just read the vertex straight off of the way we've written the model. The vertex is 2215. And what does that mean in this case? Meaning the bird population bottomed out in the 22nd year at a population of 15,000 and is now recovering. So that's a much better narrative if you are a fan of birds, because here we're telling a story that the birds were in a dire crisis and their population declined sharply. But we're sort of beginning to see the end of that decline, and they're actually starting to recover a little bit. And this is a plausible way of fitting that data. Notice this does capture the thing that the linear model didn't, which is it does capture the fact that it was declining more rapidly at first. So you can see the two models here sort of cast against each other. And you can decide which of these two you think more accurately captures the data that you actually have here in front of you. Right. Now, the natural question to ask here is, this is a math class, which is these is the right answer? Is the linear model the right one, or is the quadratic one the right one? And the answer, of course, is that birds aren't math. So neither of these models is exactly the correct one. There's a lot of things going on here. As I mentioned, we have this sort of noise in the background of the fact that the biologists are estimating the population, but their estimates are alternating in this sort of complicated way between above and below the correct population. And so our data here is really not able to tell us which of these is right. I think really if you hid the quadratic model, if you just ignored the first few points here, the linear model actually looks really good. And it's really sort of convincing that maybe this is what's actually happening. And if you look at it more holistically, the quadratic model is very plausible. That looks reasonable. But math isn't magic. It can't tell you the future. You can't say exactly which of these is more accurate. You can't say which one it is. They each give you a story that you can tell and you can look at. But in order to decide which one's actually going to happen, you're going to have to actually look there in a few years after this 25th year of the study. You're going to have to go back and look at the island and see if there's birds there or not, and see how many of them there are. So beware of this when we're talking about models and fitting models to data. You're sculpting a narrative to fit the information you have, but often the information you have can fit multiple narratives. And in order to find out sort of a conclusive answer, you're going to need more information. So sort of as a summary of this, this is one of my favorite XKCD comics. In this XKCD comic, what Randall Munroe, the author here, has done is to take the same data set here and fit a bunch of different flavors of curves to it. So we've got here a linear one and a quadratic one, which are the two ones that we've just done here. But you'll see later we have we'll talk about some of these others. So we'll talk about logarithmic and exponential models later in the course. And so you'll see just because you have the same data set doesn't mean that you're always going to fit the same curve to it. So you have to be very careful, especially when people do fit curves to data. Make sure the curve that they're fitting actually reflects the data in a reasonable way, because you'll see these people would call this overfit curves all the time, where people have given you a trend that doesn't actually really representatively show you what's actually happening. Okay. The reason I like this bird example is because I think it really does actually sort of fit in both instances. You can let yourself be optimistic or let yourself be pessimistic, and it's hard to say that either of these is really wrong. Again, if I was to really try here to give my best argument that the pessimistic case is the wrong one, I'd point out that actually on both sides, both on the left side here and on the right side here, the linear model is missing on the low side, meaning that the dashed line is below the actual observed data. And that pattern is suggestive that maybe we're missing something. Whereas here, in the case of the quadratic model that we made, we actually have a much less tendency to sort of over and underestimate at any particular time. Now, much later, we'll talk about a method of analysis for models that we'll call residual analysis, where we'll actually look at that and see when we're missing, are we missing above or are we missing below? And is there a pattern to whether we're missing above or below? And that'll give us a way to sort of develop a framework to decide which models we think are better for any particular set of data, and hopefully help us decide which model we think fits best. But for now, we just have to accept that there's going to be ambiguity sometimes. And multiple people who look at the same data set may well see different things. And it's not that the data is wrong, they're seeing the same data. It's just that data itself doesn't actually come with a narrative. The narrative, the model that we put to the data, well, that's what we read into it. And that can sometimes be read into in different ways. Anyway, that'll be all for now. I do promise, again, later in this course, we're going to talk about a bunch of other different kinds of models that you might use for different shapes of data. But I really, really hope that this is the last video that I make for this course this semester, because I'm hoping that I feel better and am able to be back by Friday, and if not by Friday, then by Monday, because as I said, Friday, there is going to be a little mini project for you to work on. So that's all for today's video. I hope to see you all real soon, and I hope you are managing to stay happy and healthy yourselves, and I'll see you all in the not too distant future. Thanks for watching, and I'll see you soon.